All right, good evening, everyone. I'm here to talk to you about breaking the x86 instruction set architecture. I think it should be a pretty fun conclusion to a really cool black hat. First off, my name is Christopher Domas. I'm a cybersecurity researcher at a place called the Battelle Memorial Institute. I really like working here. I get a chance to encounter a lot of really difficult problems. But what I think I like the most is that with the problems and people I work with on a day-to-day basis, I actually get a lot of really neat ideas on fringe areas of cybersecurity that I can sort of explore in my free time. So that's what I want to talk to you about today, is a little side project I've been working on and off for the last few months called Sifter. So this whole thing comes down to an issue of trust. And I'm going to start out with a really obvious observation. We don't trust software. And that's a really good thing. Software is horrible. So we audit software to make sure that it's working the way we expect it to work. We reverse engineer software to make sure that there's no secret functionality in it. We want to make sure Minesweeper's not dialing out to some Russian website, right? We break software. We try to find vulnerabilities, and we exploit software for the sake of hardening it to make it more trustworthy. And then we still, after all this, we still don't trust software, so we just sandbox it to try to minimize the damage when something goes rogue. But what about the processor itself? You know, the thing responsible for running all this software, the thing responsible for enforcing all the security boundaries on the system. Even though we don't trust software, the processor, we just blindly trust. And there's a reason for that. We don't have reverse engineering and introspection and auditing tools for hardware the way that we have them for software. We don't really have a way to establish trust in the processor. The best thing we have are reference manuals and specifications that describe what this processor does. We have to read these documents and just assume on faith that this is how the processor actually operates. And I think that's absolutely crazy, because we would never do that in software, right? You would never download some random executable from a website, read the README, see if the README says totally not a virus, and think, yeah, this is totally not a virus, I'll go ahead and run it. But that's exactly what we're doing with our processors. All we have to go on is the documentation that says this is how the processor operates. So why is that? Why do we blindly trust the processor even when we're so untrusting of software? Because hardware has all the exact same problems that software has. So in software, we worry about secret functionality, right? Well, hardware has secret functionality. For example, Intel infamously had what were called the Appendix H documents with the Pentium processor. This was like a secret set of documentation that described proprietary parts of the architecture that they didn't want the regular public to know about. You could only get access to Appendix H if you were a trusted Intel partner. What about bugs? We worry about bugs in software, right? Does hardware have bugs? Absolutely. The Pentium had the FOOF bug, where you could give it what was called a lock comp exchange instruction, and the processor itself would lock up. It's a serious security vulnerability. The Pentium had the FDiv bugs, wherein 1 in a couple billion floating point instructions would be off by a fraction of a percent, cost Intel about $500 million. Haswell has TSX bugs. You may have heard that they had to completely disable transactional memory support in Haswell because of bugs. Skylake has hyperthreading bugs, things that look pretty serious and could cause data corruption. You may have heard about the Risen bugs, wherein Risen processors will lock up or crash under heavy FMA3 instruction loads. We're just riddled with bugs in our modern processors. What about vulnerabilities? We worry about vulnerabilities in software. Processors have vulnerabilities too. The Sysret vulnerability on x86 allowed kernel privilege escalation on a wide variety of operating systems. The cache poisoning and memory sinkhole attacks allowed privilege escalation into system management mode on x86 processors. We have vulnerabilities galore on these processors as well. So if processors have all the same issues as software, we should really stop just blindly trusting the hardware. So what kinds of things do we need to worry about when I say we should stop trusting the hardware so much? Well, the main thing I was interested in for the purposes of this research were hidden instructions built into the processor. Basically, secret functionality that could give you backdoor or powerful access to some sort of processor internals. And this sounds almost conspiracy theory-esque, right? Like, this is crazy, but it's not all that far removed from reality. We actually have some pretty good historical examples of this kind of thing built into x86. So for example, x86 used to have what was called the ICE breakpoint instruction. This was an undocumented instruction, not acknowledged by the manufacturer, that would put the processor into a special privileged ICE mode. It used to have the load all instruction, another undocumented, unacknowledged instruction that would allow you to load secret processor registers with values that you couldn't normally get into those registers. Even looking at more recent examples, you may have heard about the API call vulnerabilities and the Microsoft x86 emulators. Essentially, Microsoft backdoored the UD0 instruction in x86 to redefine that instruction to be something entirely different, and then didn't really acknowledge that that instruction existed. So this stuff's not all that far removed from reality. The possibility of powerful hidden instructions is very real. And to sort of hit that home, if you open up x86 software developer manual guides, you look towards the back of Intel SDM Volume 2, you'll see page after page of tables that look like this. These are the processor opcode maps. They basically are supposed to tell you every instruction that exists in your processor. They tell you when your processor sees this byte, it executes this instruction. When it sees this byte, it executes this instruction. But you may notice something. If you look really closely at these opcode maps, there's something a little unusual here. There's a gap down on the bottom here. Now, this is the document that's supposed to tell us exactly what this processor does. This is the document we're basing all of our trust on, but it's intentionally leaving things out. Now, we don't have reverse engineering or auditing tools for x86. We really just have this document, and it's intentionally not giving us all of the information. So that's not a really good start towards trusting these processors, right? So my goal when I set out on this project was to find a way to sort of audit the processor, figure out what instructions are really on this thing. So how do we find hidden instructions in the x86 architecture? Well, there's a unique challenge in x86, mainly that instructions in x86 are very complex. They can be either 1 byte long, so for example, increment EAX is a 1 byte instruction, just hex 40, or they can be up to 15 bytes long, so lock, add, keyword, CS override, some complicated address, some complicated immediate value is a 15 byte instruction in the x86 architecture. So if you look at a worst case scenario of how many instructions could there possibly be in x86, if we just say what if all instructions are 15 bytes long, the maximum length, it's somewhere on the order of 1.3 undecillion possible instructions. That's a really, really unfathomably large search space, right? Which means that the obvious approaches to trying to search through this instruction set don't really work. You can't just try all the instructions. That might work on a RISC processor. That's not going to work on an x86 processor. You can't really just try random instructions. It's going to give you really, really poor coverage if you just generate random instructions to see how they execute on the processor. So you might think, well, could we guide our fuzzing based on the processor documentation? Well, there's two big problems with that. One, I think we've already kind of established the documentation isn't telling us everything. The documentation can't be trusted. If you guide your analysis based on the documentation, you're sort of going to lose right from the start. Another big issue with that, you might think, well, we saw those gaps in the opcode maps, right? Why don't we just like fuzz around those gaps? Those gaps really only tell you the first byte of the instruction. So if you're dealing with a complex instruction that exists within one of those gaps, you're still not going to be able to find it with any naive approach trying to focus just on that gapped area. We need something a lot more intelligent to search through the x86 instruction space. So our goal here, since we've got so many possible bytes in an instruction, is to quickly skip over the bytes that don't matter so that we can focus on the bytes that actually do matter. So I start out with an observation here. The meaningful bytes in an x86 instruction impact either that instruction's length or its exception behavior. In other words, the bytes that really matter are changing something fundamental about that instruction. And the bytes that don't matter tend to just be register or immediate values that don't really change anything fundamental about that instruction. So I want to find a way to focus on those meaningful bytes. And I kind of came up with an approach that would use a depth-first search algorithm to quickly enumerate the x86 instruction set. And it works something like this. We're going to guess an arbitrary x86 instruction. I'm going to basically guess 15 bytes. Let's start out with just 15 bytes of zeros. Then we're going to execute this instruction on the processor. And through that execution, we're going to look at how long that instruction actually is. In this situation, when we execute that instruction, we'll see that it's a 2-byte instruction. So then I'm going to move to the last byte of that instruction, and I'm going to increment that last byte of the instruction. And then I'm going to rerun the instruction to see how long it is again. Again, we'll see that this instruction is 2 bytes long. We'll increment the last byte, re-execute it, observe its length. Increment the last byte, execute it, observe its length. And eventually, when you increment that last byte, you're going to find something. when you execute the instruction, the length of that instruction is going to change. It just became 3 bytes now. So when you observe that the length of an instruction changes, we're going to move to the last byte of the instruction and increment it again and begin the process all over. Execute the instruction, observe its length, increment. And when you start doing this to search through the instruction set, these are the kinds of patterns you're going to find. We'll start at 0, 0, become 0, 1, and when we start incrementing, eventually our instruction grows in length. We'll keep incrementing, and eventually we'll observe another length change. So as you can sort of see here, we end up with more and more complex instructions as we drill deeper and deeper into the instruction set with this approach. Now, eventually, you're going to go through all possibilities of that last byte of the instruction, and the length isn't going to change anymore. So when that happens, when you've tried all 256 possibilities for that last byte, when that last byte is FF, you're going to increment it to let it roll over. Then you're going to move back up to the previous byte. That byte's going to become your new marker. That's what we're going to increment from now on. So we're going to increment the marker, execute the instruction, observe its length. If the length didn't change, just repeat that process. Increment the marker, execute the instruction, observe its length. And we'll keep doing this. Eventually, in this situation, that marker will roll over again, so we'll move back another byte. The marker will roll over, we'll keep moving back. And we keep doing this, continuously incrementing and moving back now until eventually, when we increment one of these bytes and execute the instruction, the length of that instruction is going to change again. So we know that we changed another fundamental piece of this instruction. So now we're going to move to the end of the instruction and start the process all over again. So what this approach does is essentially it lets you tunnel through this instruction space to quickly skip over these bytes that don't matter and really focus on the bytes that do matter. It lets you exhaustively search the bytes that actually impact the instruction execution. And effectively, that reduces your search space from 1.3 times 10 to the 36 and possible 15 bytes instructions down to about 100 million instructions, which you can search through in about a day of scanning the system. But there's a big catch here that I kind of glossed over. In order for this to work, you need to know what the length of an x86 instruction is. Now, that seems like it should be easy. It shouldn't be too hard to figure out what the length of an instruction is, but you can't just disassemble it because we're possibly dealing with undocumented instructions, right? An obvious approach, if you know x86 pretty well, might be to try to use the trap flag. So the way the trap flag works in x86 is you set the trap flag, you execute an instruction, that instruction runs, and then a trap signal is generated, and your trap handler gets control. Now, what your trap handler could do is it could look at the new instruction pointer and compare that to the old instruction pointer. The difference between those two would be the length of your instruction. It seems easy enough, but this fails to find the length of faulting instructions because faulting instructions in x86 don't actually execute. There's no change in the instruction pointer, so there's no way to resolve the length of a faulting instruction. Why do we care about faulting instructions? Well, trying to execute a privileged instruction in a non-privileged mode will generate a fault. I want to find all instructions in the x86 ISA, not just the one that exists in my current mode. So for example, loading a control register is an instruction that only exists in ring 0. The VM enter instruction is an instruction that only exists in the hypervisor. The resume instruction is something that only exists in system management mode. I want to find all of these instructions regardless of where I'm scanning from. So I need to be able to find the lengths of faulting instructions as well as executing instructions. So the solution I came up for with this was a sort of a page fault analysis. So here's how this would work to figure out an instruction length. Basically, we're going to start with a candidate instruction. We don't know how long this instruction actually is. We're going to set up 2 pages in memory. The first page is going to have read, write, and execute permissions. The second page is going to have only read and write permissions. We're going to put our instruction into these pages so the first byte of the instruction is on the last byte of the executable page, and the rest of the instruction is on the non-executable page. Then we're going to jump to the instruction to try to execute it. So here's what happens internally in the processor when we do this. The processor first fetches that first byte, that OF byte, out of the executable page. And it sees OF is not an instruction by itself. It needs more bytes for this instruction. So then it's going to try to fetch the next byte. It tries to fetch that 6A. But that 6A is sitting in a non-executable page. That means we're going to get a page fault exception when it tries to hit 6A. Specifically, we get a page fault exception with the CR2 register loaded with the address of the page fault. So CR2 is going to point to the address of that second page in memory when we get this fault. So if we receive that page fault exception with CR2 pointing to the second page in memory, we know that our instruction is longer than just that OF. So we move the whole instruction back a byte and repeat the process. Execute the instruction. The decoder is going to look at that OF, say, I need another byte, now it can successfully fetch the 6A since it's in an executable page. It's going to realize I still need more bytes for this instruction to be complete. So it's going to try to fetch that 6-0. Now we get the page fault exception again. Move the instruction back a byte and just continue this process. As long as we're getting page faults with CR2 set to the address of the second page, continue this process. And eventually what you'll find is your entire instruction sits in the executable memory. And when that happens, a lot of different things can occur. Either the instruction could successfully run, the instruction could throw an entirely different fault, or the instruction could throw a page fault just with a different value in CR2. But regardless of what happens here, in all cases, we know that the instruction has now been successfully decoded, so it must reside entirely in the executable page, meaning that we know the instruction's length at this point. So we've figured out how many bytes the instruction decoder consumed, but that doesn't actually mean that this instruction exists yet. Just because the bytes are decoded doesn't mean this instruction's real. Even non-existing instructions have to be decoded. So how do we figure out if an instruction actually exists in the architecture? Well, if the instruction does not exist, the processor is going to generate an undefined opcode exception after the instruction decode phase. So if we don't receive that UD exception, that means that this instruction exists. So the neat thing about this approach is it gives us a way to find the lengths of successfully executing instructions, faulting instructions, even privileged instructions. So even sitting in ring 3 on the processor, I can find out whether certain instructions exist in ring 0 or ring -1 or ring -2 using this approach. So I threw all this functionality into a process that I called the injector. It basically does this page fault analysis and this instruction tunneling to search through the x86 instruction set very quickly. But the injector has a really big problem. It's fuzzing the device that it's running on. So how does the injector keep itself from crashing? Well, it takes a little bit of work to make this happen. So the very first thing we're going to do to keep the injector from crashing itself is we are going to limit ourselves to ring 3. Now, that's not such a big limitation. The injector can still resolve the lengths and existence of instructions inside of other more privileged rings. So that's actually okay. But basically, limiting ourselves to ring 3 prevents catastrophic system failure for bad instructions, with the exception of very serious processor bugs. So that's nice. That's a good first step towards keeping ourselves running. The next thing we're going to do is we're going to hook all of the exceptions that these instructions that we're generating could create. So for example, in Linux, we're going to hook segmentation faults. We're going to hook illegal instruction exceptions, hook floating point exceptions, hook bus errors, and hook trap exceptions. And by hooking all of these things, whenever an instruction throws one of these exceptions, our process will get control, and it can correct the system state. And by correct the system state, I mean our process is basically going to reload the process's registers with known good values to allow execution to continue. So we're getting further, but we're not there yet. The next step is we're going to initialize all general purpose registers to 0 right before we execute these candidate instructions. What that lets us do is it lets us find or generate an arbitrary instruction like this, which writes a value to some arbitrary location in memory, and it ensures that that address calculation resolves to 0. So EAX times plus 4 times ECX is 0 as long as our registers are all initialized to 0. That ensures that memory accesses don't accidentally hit the process's address space. You don't accidentally corrupt your process data in this process. So it gets us a little closer, but x86 has some really complicated addressing forms. So for example, we can do EAX plus 4 times EAX plus some big 32-bit value. Now, even though those registers are initialized to 0, and the left half of that calculation will be 0, if that offset part of the calculation hits the process's address space, we could still corrupt our process and not be able to recover. Fortunately, we're in good shape here because of the tunneling approach to how we generate these instructions. So basically, tunneling is fuzzing 1 byte of the instruction at a time. So that offset in the memory access has to have 3 bytes of zeros inside of it and 1 byte of non-zeros. So it just so happens that all the possible offsets we can generate through tunneling don't hit the process's address space, so we don't corrupt our system state. Now, any of those other offsets do generate a seg fault exception, but that's fine. We catch seg faults and recover from them inside of our process. So we've handled faulting instructions. Now we need to think about non-faulting. instructions. Basically, the analysis needs to continue after an instruction successfully executes. So imagine that you randomly generate an instruction that says jump back 40 bytes. Well, now you're going to be executing random code, and that's going to irrevocably corrupt your process state, and the injector is going to come crashing down. We don't want that to occur. We need to systematically get control back after these instructions execute. So here's where the trap flag can actually help us. We'll set the trap flag right before we execute one of these candidate instructions, and in our trap handler, we'll reload the registers to some known good state. So regardless of what that instruction did to the registers, we'll restore them to good values. So with all these approaches, by limiting ourselves to ring 3, by handling all the possible exceptions, by initializing registers and maintaining registers in a known good state, and trapping these executions of these instructions, the injector is actually able to survive now. So at this point, we've got a way to search the x86 instruction space, but now how do we make sense of the instructions that we're actually executing? So I designed what I called the sifter for this. Sifter is basically a wrapper around the injector, and the sifter's job is to parse and process the results of the injector and look for anomalies in the execution. Now, what do I mean when I say an execution anomaly? Basically, what I want to find is anywhere where what the processor actually does deviates from what the processor manuals say the processor should do. Now, the easiest way to accomplish that is to find some sort of ground truth that represents the processor manuals. So what I did for this is I just used a disassembler as my ground truth, capstone in this situation. The idea here being that the disassembler is written based off of the processor documentation. So if I find some difference between the actual execution and capstone, that indicates a difference between actual execution and documentation. So how do we actually pull out interesting anomalies then, now that we've got this disassembler as our ground truth? Well, we can pull out undocumented instructions this way. If the disassembler doesn't recognize a byte sequence, but the instruction generates anything other than an undefined opcode exception, that indicates that this instruction exists on the processor, but it's not documented. We can also pull out software bugs using this approach. Basically, if the disassembler recognizes an instruction, but it thinks it's one length and the processor says it's a different length, that usually indicates that there's some sort of bug in our disassembler. We can also find hardware bugs with this approach. Now, there's no really good heuristic for pulling out hardware bugs. Basically, everything just goes haywire when there's hardware bugs. And I'll show what that looks like a little bit later on. It requires a little bit of manual analysis to identify. So I'm going to try to demonstrate this SandSifter tool for you here. What I'm going to do is I'm going to fire up SandSifter and see if we can adjust this. So what we see here is SandSifter scanning through the x86 instruction set architecture. On the top here are the instructions that SandSifter is currently injecting into the processor. On the right is the raw byte sequence that it's generating. And if you watch that byte sequence closely, you can actually sort of see how this tunneling process is working, how it's incrementally building more and more complex instructions by modifying the last byte of the instruction. This highlighted part in white here is indicating the actual observed instruction length as seen on the processor itself, whereas this part on the left here is showing me what capstone thinks the instruction looks like. In other words, what the documentation says this instruction is. If we let this run for a while, we'll actually start seeing it dumping out a couple of anomalies in the window down here. Essentially, it's looking for places where the documentation and the actual execution differ. Now, tunneling is a really good way to very thoroughly go through every instruction in the x86, or every useful instruction in the x86 architecture, but tunneling is not the fastest thing in the world. So if I really want just fast results, I can actually switch this thing over to totally random fuzzing by changing modes here and just generating completely arbitrary instructions. We won't get as good coverage of the instruction space, but we'll get some really quick results. So what you see dumping out in the red on the bottom is undocumented instructions, secret instructions that are sitting in my CPU right now. And I find this really unsettling because we're basing all of our trust off of these documentation for the processor. And there are a lot of things in that processor that they're not telling us about. Now, if you let this thing run overnight, it'll basically complete the actual tunneling approach, complete its total scan, and at the end it'll dump out everything it found. So on most modern x86 processors, it'll find a couple million of interesting things. Now that's a lot to sift through by hand. We need some way to quickly make sense of this kind of information. So I built what I call the summarizer. It will take all the results of SandSifter and try to summarize it in a digestible form. So this is a breakdown of the key instructions that I found in a scan of a VIA Nano processor. So I can scan through here and basically see different categories of instructions. So for example, it's telling me on this VIA Nano processor, there was a set of instructions that started with OF1B that weren't documented. It found 64 instructions in this category. And then I can start drilling down into these sets of instructions in a little bit more depth. So for example, here I'm examining one of the undocumented instructions that found OF-A7C3. It's telling me that when this instruction ran, it generated a trap exception, and then it gives this instruction to 3 different disassemblers. None of these disassemblers recognize what this instruction is, which is a very, very strong indicator that this instruction is not documented and is not known by anybody, even though it's running on our processor. So at this point, we have a way to systematically scan our processor for secrets and bugs, and I think that's really cool. So I scanned 8 of the test systems that I had in my library, and I wanted to share with you what I found on these systems because I came up with a lot of really interesting results. First, I found hidden instructions on every single x86 chip I scanned. I found ubiquitous software bugs in all sorts of different programs. I found flaws in enterprise hypervisors, and I found some very security critical hardware bugs on x86 processors. So let's start with the one I set out to find. I set out to find these hidden instructions on x86 chips. So I started with scanning an Intel Core i7 processor. This processor was manufactured around 2012. The first set of instructions I found on the processor aren't terribly interesting. OFOD, OF18, OF1A, OFAE. All of these instructions are undocumented for certain combinations of bits inside of that instruction. But those combinations of bits still execute on the processor. Now, some of these instructions, Intel has very recently updated their manuals to actually include. So for example, OF18 and OF1A became documented by Intel in their December 2016 edition of the reference manuals. But I ran this test on a processor manufactured in 2012. These instructions were sitting around in my processor undocumented, secret, for a very, very long time. Other instructions found on this processor, on the other hand, DBE0, DF, F1, C0, D0, D2, F6, F7, entire classes of instructions still don't appear anywhere in the reference manuals. We have no idea what these instructions actually do. So I started scanning other systems. I scanned an AMD Geode system. These are the undocumented instructions I found on AMD. Now, when I started scanning systems or processors from different manufacturers, I noticed some interesting patterns. There were a lot of overlaps in the undocumented instructions across different manufacturers, which means even though that we don't know what these instructions do because they're not in the documentation, the manufacturers are coordinating on what these instructions actually do. So for example, on an AMD system, I found the same DBE0, DBE1, and DF instructions that I found on Intel systems. But the really interesting places that came up were the places that didn't overlap, where there was some unique instruction only on this version of the architecture. So in this AMD chip, I found a set of unique instructions at OF 4080, followed by some final bytes. Now, some versions of these instructions for that final byte were documented, but the vast majority of them that actually executed on the processor were not documented by AMD. I scanned a VIA system, and we found sort of the same things, a lot of overlap with other undocumented instructions from other manufacturers, but then unique sets of instructions that only appeared on VIA. So specifically, the OF-A7 group on VIA is actually VIA's proprietary padlock instructions. It's a set of cryptographic instructions that only exist on VIA chips. And VIA documents the padlock instructions, but they don't document OF-A7 C1 through C7. So that is a set of cryptographic instructions on this processor for which there is no documentation. We have no idea what they actually do. So as far as like trying to figure out what do these things really do, some of these have been reverse engineered. If you dig around enough online, you can actually find people who have stumbled across some of these instructions before, looked at how the register values are changing on these instructions, and inferred what that instruction behavior is. But some of these instructions have absolutely no record at all. No record in any of the reference manuals from the manufacturer, and no other record anywhere else online. So there's no way to tell what these things really do. And I find that pretty unsettling in terms of trusting our processors, right? So let's look at a totally different thing. I didn't set out to find software bugs, but I ended up finding a lot of really interesting ones. So there's an issue I faced. My SAN sifter is forced to use a disassembler as a ground truth. And I tried a lot of different disassemblers as ground truths, and all of them were absolutely littered with bugs. So for the most part, the bugs in disassemblers only appeared in a couple of the disassemblers that I tried, so it wasn't especially interesting when only one disassembler has its own class of bugs. We should fix those bugs, but that's not like a security critical thing. But we did find some interesting bugs. We found some bugs that appeared in literally every tool that we threw this thing against. And you can actually use these bugs to your advantage if you're an attacker. So two of the more interesting ones I found were these jump and call instructions. So in the 64-bit version of the x86 architecture, theoretically, E9 is a jump instruction, E8 is a call instruction, and 66 is what's called a data size override prefix. And what 66 is supposed to do is it's supposed to change the default operand size of that instruction. So normally E9 and E8 take a 32-bit operand. So 66 is supposed to change that either to a 16-bit operand or to a 64-bit operand. Turns out on x86 it does neither, or on Intel processors it does neither. 66 is just ignored by the processor. But nobody expected that. Everyone parses these instructions wrong. So what does that mean? Well, all these tools have this exact same bug in them. I tried this with IDA, Valgrind, GDB, Objdump, Visual Studio, Capstone, QEMU, and about a dozen others, and they all had this bug. So let's look at this instruction in IDA, for example. You'll see that IDA is parsing this as a 4-byte instruction because it thinks that this 66 override prefix changes this to a 16-bit operand. That's not the correct behavior. This instruction is not being parsed correctly by IDA, our reverse engineering tool. Let's look at it in Visual Studio. Visual Studio has a different version of the same bug. You'll see that it actually does recognize, even with the 66 override prefix, this is a 32-bit operand, but it thinks the 66 override prefix causes the jump target to be truncated to 16 bits. That's also not the correct behavior. Visual Studio is not correctly resolving the target of this jump instruction. And an attacker can actually use this to mask malicious behavior in software. You can basically use this to throw off the disassembly so that our analysis tools don't see malicious instructions. As an example of that, this is looking at the 66 jump instruction in Objdump. So what I have here is that 66 jump, and Objdump is misparsing that instruction. It thinks it's a 4-byte instruction when it's really a 6-byte instruction. What that means is that Objdump has also misparsed all the subsequent instructions since it's now off by 2 bytes. So even though Objdump and GDB in this situation will see a jump instruction followed by an add, followed by an add, followed by a move abs, that's not the real instructions that are there. What's really going to happen here is this is going to be a 32-bit operand that's going to jump into the middle of one of these move abs instructions and execute a malicious instruction embedded in this immediate value. Sort of to highlight the implications of this in terms of our analysis tools, I wrote a little malicious program that's going to operate differently inside of QEMU versus running on a bare metal processor. So what I'm going to do is I'm going to SSH into my QEMU VM, and I'm going to run this program. This program is very, very simple, but it starts out with one of these 66 jump instructions. QEMU misemulates that instruction, and it thinks that this program is totally benign because that's the execution that QEMU sees. But now when I exit out of my VM and I run this exact same thing on bare metal, that instruction executes differently. We now get malicious behavior from our program. And I think the neat thing about this is there was no QEMU detection logic inside of this program. It just started out with that one malformed jump instruction that caused everything else in the emulation to go haywire. So this is an interesting bug. And I was curious about why does everybody screw this instruction up? And I think the answer is AMD processors actually obey that instruction. That 66 override changes the operand size to 16 bits on an AMD processor, whereas Intel processors are actually ignoring that prefix. So it's a really interesting difference in the architecture. And whenever we can't agree on a standard for our architecture, bad things start to happen. So the last major time this happened, when Intel deviated from AMD specifications, it resulted in what was called the Sysret bug. It caused a kernel privilege escalation vulnerability in nearly every major operating system because of a very small change between the way these two processors operated. So you might think, well, why don't we just update all of our tools to support the correct or the more common Intel behavior? Since Intel's 95% of the market share, let's just go with what Intel does. Well, the problem is either Intel or AMD are going to be vulnerable because of this difference. There's no winning here. And I think it really just shows how impractically complex this architecture is when tools can't just process or parse simple jump instructions correctly. So those are some of the interesting software bugs. There are a lot more than that I don't have time to cover. I also found some really cool hypervisor bugs. So when I was in the early stages of this research and trying to find interesting things in the instruction set, I got tired of waiting a day for these instruction scans to complete. So I added multi-core support to the scanner. And I thought, well, wouldn't it be neat if I could just have 20 cores churning away on the instruction set at once, then I could scan in an hour what used to take me a day. So I rented an Azure instance with 20 cores so I could run these instruction searches. But really quickly, I found out that these scans weren't working inside of Azure. So basically, Azure had this really interesting bug where the trap flag is missed when you execute a CPU ID instruction. So if you have a CPU ID instruction and you execute it with the trap flag set, what's supposed to happen is the CPU ID causes a VM exit. The VM is then responsible for emulating that CPU ID instruction. And the last thing it should do, the last thing the hypervisor should do is check, is the trap flag set? And if it is, it should inject a trap exception into the guest. Now, Azure's forgetting that last step of checking that trap flag and injecting that exception. So sort of as a demo of this bug in Azure, I've got a little test program here, and when I run this thing on bare metal, here's what it's going to do. It's going to execute a series of instructions. It's going to execute a CPU ID followed by a NOP, followed by a NOP, and the trap flag is going to be set during that CPU ID execution. Now, what we expect to happen is we expect to get a trap on that first NOP instruction, and what we really get is a trap on that first NOP instruction. But if I SSH into my Azure instance and run that exact same program, we're now going to get entirely different results. We executed CPU ID NOP NOP, and we expected a trap on that first NOP. What we got was a trap on the second NOP. The hypervisor forgot to emulate the trap exception. Now, this is not a security critical bug. This is a very, very minor thing, but it's always a little unsettling when the hypervisor is not properly emulating some of the very basic functionality of the underlying architecture. So that takes us to hardware bugs. I think the most interesting results of this little research effort. Hardware bugs are troubling because if you have a hardware bug, it basically means you have that exact same bug in all of your software. And hardware bugs are very difficult to find. They are very difficult to fix. So hardware bugs, even when they're small, are never a good thing. So I started out scanning several Intel processors. And unfortunately, I didn't find anything terribly interesting here. I found the FOOF bug on a Pentium processor. So FOOF was a lock comp exchange instruction that would lock up a Pentium processor. This is a well-known bug from very old processors. So this was a little anticlimactic, but it did show that this technique is able to find these malformed instructions that cause bad things to happen. So it was good validation. So the next thing I scanned were some AMD processors. I noticed an interesting thing on AMD. Namely, on several of these processors, they can generate an undefined opcode exception prior to completing the instruction fetch. So I dove into AMD's reference manuals and found that this is not the correct behavior for this processor. A page fault exception during the instruction fetch should take priority over an undefined opcode exception. So in our instruction search, where we have the last few bytes of an instruction sitting on a non-executable page, we should be getting a page fault exception, not an undefined opcode exception. So that's not the correct behavior. It's a minor thing, but that is a processor errata. Until when I was making this presentation, I looked at the newest version of the AMD documentation. And in March 2017, just a couple months ago, somebody at AMD must have stumbled across this, and they added this little footnote to the processor interrupt exception priority tables that basically allowed for this situation. Now, I think this was a little bit of a cop-out. If your processor has an errata in it, and then you update the documentation to allow that errata, is it still an errata? I think it is, but apparently this is allowed in the newest version of the AMD manuals. I scanned a Transmeta processor. Transmeta is not especially popular anymore, but they were kind of interesting a couple of years back. I found some interesting results in the Transmeta, where this series of instructions, OF71, 72, or 73, could generate a floating point exception during the instruction fetch phase. So if you had a floating point exception pending and you try to execute one of these instructions, you would get a floating point exception before the instruction was completely fetched. That's also not the correct behavior. The correct behavior here is to get a page fault instruction during the instruction fetch. So again, very, very minor errata that you would never see in any normal situation, but it's all when there's a bug in hardware. So that brings me to the last hardware bug that I found in this research, and this is, I think, the most interesting one. So I found this on one processor, essentially a halt and catch fire instruction. What I mean by that is it is a single malformed instruction, and if we run this inside of ring 3, the least privileged ring on the processor, it will lock the processor entirely. I wanted to be really, really sure that this wasn't a kernel bug that I was seeing, so I tried this on 3 different Linux kernels, 2 different Windows kernels, and always got the same results: a complete processor lock when we execute this one bad instruction. To be really sure that it wasn't a kernel bug, I developed a loadable kernel module in Linux that would hook the interrupt descriptor table, hook all the exceptions that can possibly occur on the processor, and dump exception information to serial whenever an interrupt on the processor occurred. I was a little bit worried that maybe it was just an interrupt storm that was making it look like the processor was locked. Based on this debugging, it sort of validated that this is in fact a total processor lock on an unprivileged malformed ring 3 exception. Now, unfortunately, I found this 2 weeks before this presentation, which means the vendor has not had time to respond to this issue, and I'm not going to shoot them in the foot here. There's really no details available on what chips or vendors or actual instruction caused this issue right now, but I do want to give you a quick demonstration of this ring 3 processor DOS on this system. So what I've got here is I've got Debian booted. You can see it can run any normal program, but if I run my a.out program, a.out only contains one instruction. It contains this one malformed ring 3 instruction. And now when I run a.out, the processor entirely locks. I don't mean the process locks, I mean the processor locks. We can try to kill the process with Control-C, it won't respond. We can try to change run levels to get into some more simple state. The system won't respond. We can try to use the Linux magic Sysret keys. The system won't respond. That processor is completely done executing instructions and is hard locked at this point. So I think this is a really interesting find because this is the first such attack found in 20 years. The last time this happened was on the original Pentium processors with that foof instruction that could lock the processor. I don't think anything like this has been seen in the 20 years since. But I also don't want to make it sound like the sky is falling. This was found on one very esoteric processor that is not used in widespread production. I think it's mostly interesting from an academic perspective that we have a tool that is able to find these kinds of things now. And this should be, I think, obvious. This is a significant security concern, right? If an unprivileged user can mount a DOS attack against the processor itself, that's a real problem. So I'm hoping I can release details for this within the next month or so. Stay tuned. I'll be posting information about this if the responsible disclosure goes okay. Like I said, I wanted this to be a tool that everybody could actually use, that people could use to check their own systems for problems. So I open sourced this as the Sifter Scanning Tool. It's on GitHub now, github.com/xor/eax/SANSifter. I'm just remembering right now, I actually forgot to click the public button before this talk. So in about 5 minutes after the talk, this will be available to you. So I encourage you to go check this thing out. Audit your processor, figure out what are the secret instructions sitting in your system right now. Break disassemblers, break emulators, break hypervisors. Find these halt and catch fire instructions. Now, the system I found that on didn't literally halt and catch fire, but who knows, maybe yours will. I think that would be awesome. So hopefully you'll be able to find something interesting if you try this tool out. And I really want to emphasize, I've only scanned a few of the systems that I have right now, and this is just a tiny fraction of what I found on those systems. It's just what I could cram into a 45-minute presentation, so who knows what exists on your system. So I encourage you to check your system. If you're not sure about the results that you're seeing, feel free to reach out to me. I can help you interpret those. But the real point here, even if you don't use a tool, is don't blindly trust the specifications anymore. Up until now, we've been forced to blindly trust specifications because we had no way to look into what the processor was actually doing. And I think now that's what SANSifter gives us. It's a primitive first step that allows us to introspect this black box that is at the heart of all of our systems. And I think that's a really important first step in terms of establishing trust on these processors. So with that, sort of wrapping everything up, one more time, that link is github.com/XOR-EAX. That's the Sand Sifter project. You can also find some other fun things that I've worked on over the last few years. For no reason at all, I wrote a single instruction C compiler that's on there. So if you're curious about how that works, you can check it out. I've got some fun stuff from manipulating program control flow to mess with people in IDA. A couple years ago, I released an architectural privilege escalation vulnerability on x86. You can find that code there as well, and just lots of other miscellaneous projects I've tinkered with recently. So I hope you'll check that out. I'd really, really like to get feedback and ideas from people on this work so that I can update this and make this more useful for everyone. If you've got any of that, I'd love to talk to you after my presentation, or you can reach out to me on Twitter, XOR-EAX. I'll be posting more information about that Ring 3 DOS instruction in the near future, or you can reach out to me on email. So that's all I've got. I'd love to talk with you off stage as soon as this is over. Thank you everyone for attending.